Welcome to G Fun Facts Online. Today we are diving deep into a discovery that completely changes our understanding of the nearest star to Earth. For generations, we have looked at the Sun as a massive, celestial cannon. We viewed it as a simple, violent engine that generates energy and blasts it outward in a one-way stream. We know it constantly emits the solar wind, that stream of charged particles bathing the solar system, and we know that occasionally it coughs up massive clouds of plasma known as coronal mass ejections, or CMEs. The prevailing assumption in heliophysics, the study of the physics of the Sun, has been incredibly straightforward regarding these ejections. The logic was that once this superheated material leaves the solar surface with enough energy, it is gone forever. It was thought to be a ballistic event, like a bullet leaving a gun, destined to ripple across the solar system until it fades into the interstellar medium. But a groundbreaking discovery has shattered this paradigm. We now have definitive evidence that the Sun is defying our understanding of stellar ballistics. It is performing what scientists are calling a magnetic U-turn. Recent observations, specifically from NASA's Parker Solar Probe, have revealed that significant portions of the material we thought were lost to space are actually being dragged back down into the solar atmosphere. This is the phenomenon of solar ejecta recycling. To understand why this is such a shock to the scientific community, we need to look at the environment where this is happening. The solar corona is the Sun's wispy outer atmosphere. It is a place of unimaginable hostility, burning at over 1,000,000 degrees Celsius, which is actually far hotter than the surface of the Sun itself. In this realm, gravity is not the ruler. Magnetism is king. Traditionally, solar physicists have modeled the Sun's magnetic field by dividing it into two main categories to make sense of the chaos. First, you have closed field lines. Imagine these as loops that arch out from the surface and snap back down, trapping plasma in glowing structures often called helmet streamers. Second, you have open field lines. These are the magnetic highways that stretch out infinitely into the solar system, allowing plasma to escape as the fast solar wind. When a coronal mass ejection occurs, the old model described it as a massive rupture. We thought of it as a magnetic bubble bursting outward, tearing through those overlying fields and escaping forever into the void. This was the outflow-only myth. The Parker Solar Probe changed everything, because it went where no spacecraft has gone before. It didn't just look at the Sun from a distance, it grazed the solar atmosphere, diving within just a few million miles of the surface. On board, it carries an instrument called the Wide Field Imager for Solar Probe, or WISPR. As the probe looked at these eruptions, WISPR captured something that should NT have been there. Instead of a uniform flow of particles rushing away from the Sun, the probe saw distinct blobs of plasma stopping, reversing their course, and raining back down toward the Sun. This was the U-turn. The Sun was effectively drinking its own exhaust. So how does a star reclaim material that is moving at millions of miles per hour? The mechanism behind this is a violent ballet known as magnetic reconnection. This is the engine of the recycling process. When a CME erupts, it pushes through the Sun's existing magnetic field lines. You can imagine a rubber band being pulled and stretched until it finally snaps. In the chaos of a solar eruption, these broken magnetic lines do not just dangle loosely, they seek to repair themselves. This repair process creates a phenomenon scientists have dubbed the cosmic vacuum cleaner. It happens in three specific stages. First, there is the tear. The CME punches a hole in the magnetic canopy, dragging field lines out with it. Second, there is the reconnection. Behind the departing cloud of plasma, those stretched magnetic field lines snap back together. This is the critical moment. The reconnection point acts like a pair of cosmic scissors, fusing the lines back into a closed loop. Third, and most importantly, is the inflow. As these new loops snap shut, they contract rapidly downward, like a slingshot released in reverse. This rapid contraction creates a vacuum-like effect, dragging huge blobs of plasma, material that was moments away from escaping, back down toward the solar surface. These returning blobs, now officially called inflows by researchers, are not a gentle mist. They are torrents of magnetized plasma raining down at supersonic speeds, crashing back into the lower corona. It is essentially a waterfall of fire falling back into the star. Now, if you follow space news, you might be confusing this with another phenomenon called switchbacks. It is crucial to distinguish between the two, as they tell us different things about the Sun's behavior. Switchbacks, which were also confirmed by the Parker Solar Probe and the ESA Solar Orbiter, are kinks in the magnetic field itself. Imagine cracking a whip. The wave travels down the whip, but the material of the whip stays connected. That is a switchback, a temporary reversal of the magnetic field direction traveling outward. Solar ejecta recycling, or inflows, is different. This is the actual physical movement of matter. It is the plasma itself turning around and falling inward. While switchbacks show us that the solar wind is turbulent and kinky, recycling inflows show us that the Sun is structurally self-regulating. They are likely related, of course. The same reconnection events that snap loops shut to cause inflows might be launching switchbacks outward as a byproduct. It is a messy, chaotic exchange where some energy escapes as a kick, which is the switchback, while the mass is dragged back home as the inflow. Why does this matter? Why is this rewriting the textbooks? First, it solves the missing mass mystery. This has been a long-standing accounting error in solar physics. For years, our mathematical models of CMEs suggested that these eruptions should strip the sun of mass faster than what we actually observed. If the sun were constantly losing as much material as the equations said, the solar wind should be denser, and the sun's evolution might look different. The U-turn explains the discrepancy. The sun is a conservationist. A significant percentage of the mass involved in an eruption, sometimes as much as half, never truly leaves. It is recycled back into the lower atmosphere, where it is heated, mixed, and primed for the next eruption. This suggests a stellar ecosystem where plasma is caught in a continuous loop of eruption, reclamation, and re-eruption. But beyond the physics, this has profound implications for us here on Earth, specifically regarding space weather. We rely on technology that is vulnerable to solar storms. The realization that the sun recycles its ejecta changes how we predict these storms. Consider the trajectory of a solar storm. When we see a CME erupting toward Earth, we rush to predict its arrival time and impact strength. However, if a large chunk of that CME is dragged back into the sun, the ghost of that drag acts on the material that does escape. The U-turn process acts like a magnetic anchor, slowing down the escaping CME or altering its direction. This could explain why some solar storms arrive later than predicted, or miss Earth entirely. They were effectively held back by the sun's attempt to recycle them. Furthermore, there is the loaded gun effect. The material falling back down doesn't just disappear. It crashes into the solar surface, dumping massive amounts of kinetic energy. This impact can destabilize other magnetic structures. It is like throwing a rock into a pond. But the ripples are magnetic shockwaves. These impacts can trigger secondary eruptions. The recycling process essentially reloads the solar cannon, creating a chain reaction of storms. Understanding this could help us predict clusters of solar flares that often confuse forecasters. This discovery is not just about our sun, it is about star physics in general. If our sun does this, it is highly likely that all stars do. This affects our understanding of stellar mass loss, which is a critical parameter in determining how fast a star dies. For active stars, like the red dwarfs that host many of the exoplanets we have discovered, this recycling might mean they retain their atmospheres longer than we thought. However, it also implies their surfaces are even more violent and chaotic due to the constant bombardment of returning plasma. The discovery of solar ejecta recycling serves as a powerful validation of humanity's daring missions to touch the sun. The Parker Solar Probe and Solar Orbiter are operating on the bleeding edge of technology, enduring heat shields that glow cherry red to bring us these truths. As the sun approaches the peak of its 11-year activity cycle known as solar maximum, these recycling events are expected to become more frequent and violent. Future observations will aim to quantify exactly how much mass is saved versus lost. We are learning that the sun is not a simple light bulb or a fire that burns only outward. It is a complex breathing engine that inhales almost as violently as it exhales. The magnetic U-turn is a reminder that in the cosmos, even the most powerful forces are bound by invisible tethers, recycling the fires of creation in an eternal, violent dance.